Level 2, number 2. This one has an inclined plane. And it has a box here, a 60 kilogram box. 40-degree angle. And then it has a 5-meter height over here. And it says calculate the work. Oh, and it also has a mu of 0.3. Calculate the work done. Well, okay. So, work is the force that we apply times the distance that we apply it. So in this case, we are going to be applying a force, pushing up on this, up the ramp, and the distance, I'll put the distance in a different color, is going to be the distance from the bottom of the ramp up to the top of the ramp. That's the D we're after, which is actually the hypotenuse of the triangle. So what we need to do is we need to figure out the D, and we need to figure out the F applied. The D isn't too bad. We can use trigonometry. If you look at the triangle, then sine 40 equals opposite, which is the 5-meter height, divided by the hypotenuse, which is the D of our triangle. Sine 40, right? So then D times sine 40 equals 5. And then that means that D is 5 divided by sine 40. I'll grab my calculator here and we'll figure that out. 5 divided by the sine of 40 is about 7.8 meters if you round it off. Okay, we got the D down, and that was just by using triangle math. How do we get the F applied? Well, I'm going to erase that D because it's kind of in the way now. There. How do we get the F applied? Well, guess what? We do everything we learned in our previous unit. We have to label all the forces on this picture. So we have a normal force. We have a gravity force down, Fg. And because of our mu, there will be a friction force that's working against us as we push up the ramp. And then guess what we have to do? Everything we learned before. We have to resolve the gravity into its components, Fgy and Fgx, like we did before, using the 40-degree angle. That'll be right here. Then we have to do F net y and F net x, and we work these out, and when we're done, out's going to pop F applied. And you're going to have a nice number, which you can then put in here along with the D and figure out the work that's done. Now I want to caution you, when we do work, the formula is actually F applied D cos theta. Because sometimes when we push on things, we push in a different direction than they move. Like we push a box along the ground, you might push on a downward angle, but the box moves in a different direction. And so this cos theta is the angle between the force that you're pushing with and the distance vector, the displacement vector. So it's the angle sort of right here between those two lines, right? It's this angle right here. But you only need to apply this if your F applied is at a different angle than your displacement. A lot of people see the theta and they go up here and go, oh, look, I have an angle, and they want to stick that in here because it's a theta, but it's not the same theta at all. This is the angle of a triangle. Look at the applied force, which is right up here, and the direction that you're moving this up the block, they're in the same direction. So when you do your calculation, where was it? Right here, you don't need to apply an angle because there is no angle between the F applied and the D. Even though you're on an inclined plane and there's an angle in the question, it's a different angle, it has nothing to do with this. The reason that you have that angle, of course, is to do all your FGY and FGX, and that's where that will come into play when you're doing your F net forces to get F applied. But once you get the F applied, you've already used that angle, and you don't need to use it again. So what you can do is not do this part, just F applied D. You've got the D that you figured out, and you're going to use these two things to figure out your F applied.